Hello and welcome to the extended presentation of our paper, A Fast and Compact RISC-V Accelerator for Ascon and Friends, by my colleague Robert Primas and myself, Stefan Steinegger. So the motivation behind this paper was to reduce the area overhead compared to dedicated coprocessors. And we also wanted to select a versatile building block that can be used for a wide variety of applications, ranging from authenticated encryption over hashing to pseudorandom number generation. And we selected the versatile building block Ascon-p that is used by both Ascon and Isap. If the accelerator is used in the Isap mode, we get authenticated encryption with associated data with hardening against implementation attacks, which is also a desired feature in the NIST lightweight crypto competition. And it covers both power analysis and fault attacks, and there's no need for dedicated protected hardware building blocks. Before I go into detail with our accelerator, I briefly want to go over some background information. First, we've got Ascon. Ascon is a sponge-based authenticated encryption with associated data scheme. It was the first choice in the CISA competition in the lightweight category, and it currently also competes in the NIST lightweight crypto competition. It operates on a 320-bit state that is divided into 5 64-bit lanes. It operates at the rate of 64 or 128 bits, depending on the configuration used, and it makes use of the permutation function Ascon-p. Ascon can do authenticated encryption, hashing, and pseudorandom number generation. You can see the Ascon encryption process on this slide. And as you can see, it is divided into 4 phases. First, you've got the initialization phase, that is followed by the associated data absorption phase, followed by the plain text absorption phase that also results in the cipher text. And last but not least, we've got the finalization phase that results in the tag. And as you can see, we've got the p to the power of a and p to the power of b blocks that are calling the Ascon-p permutation function either 12, 6, or 8 times, depending on the configuration in use, and also the phase the Ascon-p function is called. Hashing works in a similar manner, but I won't go into detail with it in this presentation. Secondly, we've got Isap. Isap is a mode for authenticated encryption, and the great thing about it is that it offers hardening against various physical attacks at the mode level. And this includes differential power attacks, differential fault attacks, statistical fault attacks, statistical ineffective fault attacks. It is a 2-pass scheme and is also currently in the second round of the NIST lightweight crypto competition. The nice thing about it for our accelerator is that 2 out of the 4 parameterizations are based on the permutation function Ascon-p. Now that I've mentioned Ascon-p, I should elaborate what it is about. Ascon-p transforms the state in 3 steps. First, we've got a round constant addition, followed by a substitution layer, followed by a linear layer. And the nice thing is that it is versatile and flexible. It is used in the Isap A128A, Isap A128 configuration, as well as Ascon, Ascon hash, and Ascon XOF. The versatility and flexibility of the Ascon-p permutation function and its use in a range of cryptographic primitives makes it a great target to build an accelerator for it. And typically you would do that with a coprocessor design, and that means that the coprocessor is only loosely coupled and connected over a bus, for instance an AXI bus, but that would also require to have internal sets of registers, and that would increase the overall area consumption of the chip. However, coprocessors are great if there's a lot of processing performed on a little amount of data, but they're also less flexible. So we chose a different approach. We wanted to reuse parts of the register file and implement only the combinational logic of the Ascon-p permutation. The Ascon state has 320 bits, and that means that we need either 10 32-bit registers or 5 64-bit registers. If we take a look at the ARMv7 or RISC-V RV32E specification, we can see that even for these small chip designs, we have 16 registers available. That also means that the state fits completely in the CPU registers, and if we reuse these registers, we can reduce the overall area consumption. It also makes it possible to integrate it tightly and thus make it available as a new custom instruction that is easily usable by software. It also means that the mode remains entirely in software, and it can act as a basic building block for any Ascon and Isap implementations that make use of the Ascon-p permutation. So we want to basically add the Ascon-p permutation function to a CPU core, and there we chose the RISC-V core, or how it is now called, the CV32E40P core. It is a 32-bit RISC-V CPU, and it implements the RV32I ISA, and it also features the multiplication and the compressed instruction extension, as well as an optional floating point extension. It features 32 general purpose registers, and it also has some additional instructions for digital signal processing, and it operates using a 4-stage pipeline. So to add our accelerator, the necessary changes we need to do are to define an instruction encoding, do some small modifications to the register file, and also to the decode stage. So for the instruction encoding, we chose an I-type instruction, and the I-type instruction gives us a 12-bit immediate, and there we can encode the round constant using 8 bits, and also the number of rounds using 3 bits. And optionally, we can also specify the NDNS, so we can perform NDNS swaps, which can be done very efficiently in hardware and take a lot longer in software. The RS1 and RD fields of the instruction, as can be seen on the bottom, remain unused for our use case. So for the register file, we mentioned that we require 10 32-bit registers, and that's typically more than, and we need them. That's typically more than is available in parallel on small CPU designs. At least if we want to select them dynamically. But so our solution is that we don't necessarily need the dynamic register selection, and therefore we define a fixed subset of these 32-bit general purpose registers as our Ascon-p that can be used as double as our Ascon-p registers. And we can then toggle them between the read-write port of the register file and our accelerator. And as a note here, each of the, since we have only 32-bit registers, each Ascon-p 64-bit lane is split into 2 registers. The result of this can be seen here. So we have our general purpose register file in the center. And as you can see, 2 register files make up 1 lane for the Ascon-p accelerator. That performs its permutation and then forwards it to the right side of the register file, where some multiplexers only do a simple selection between the usual write port and our Ascon-p output. For the decode stage, we need to add our instruction to the decoder, so the CPU knows about our instruction. And we also add our single cycle Ascon-p accelerator. So the Ascon-p instruction is simply enabling the accelerator and then toggling the register inputs, to the accelerator output. A limitation of this approach is that on this specific CPU, the ALU and the load store unit forward the results to the next instruction. So to work around that, Ascon-p registers must not be altered the cycle before the instruction is executed, and Ascon-p registers must not be loaded in the 2 cycles before the instruction is executed. The overall integration on the RISC-V or CV3240P CPU can be seen here, and you can see the RISC-V core with its 4 pipeline stages, and in the decode stage, instruction decode stage, we add our Ascon-p accelerator. Once it receives the signal from the decoder, it will update the specified defined general purpose registers, and you can also see that the load store unit and the execute unit forward the results to the decode stage, and that's why we need, and that leads to the one limitation I mentioned on the previous slide. So what does that mean for using the instruction? Here you can see the Ascon main data processing loop. And as you can see on the right side, that's basically the plain text absorption phase, and that also results in the cipher text. So we've got our load words 2 times 2, because we're reading 2 plain text blocks. We're then XORing it with with 1 lane of the state and storing the cipher text. And after that, we execute the Ascon-p permutation function 6 times. That's the part of the p to the power of b block. And then we do it for each of the message blocks, plain text blocks. Now that we've seen how the Ascon Accelerator is built and built into the RISC-V CPU, we should also talk about the performance numbers and basically what we gain from doing it from doing this approach. As we can see in this table, we tested using a range of Ascon and Isap implementations. And we've got our Ascon C implementation compiled with the -03 flag, and also one optimized for size with the OS flag. And we have our Ascon assembly implementation that makes use of our Ascon permutation hardware instruction, as well as an Ascon hash assembly implementation using our hardware instruction. Last but not least, we also have our Isap A128A C implementation compiled with the 03 flag, and the Isap A128A assembly implementation with the hardware instruction in use. And we can see that in terms of speed, this Ascon C implementation compiled with the -03 flag results in 164 cycles per byte for short 64-byte messages, which then gets down to 108 at about 108 cycles per byte for long messages. When we compare that to our Ascon assembly implementation that uses our hardware instruction, we can see that this brings it down to only 4.2 cycles per byte for short messages, and down to 2.1 cycles per byte for long messages. In terms of binary size, we can also further reduce the hardware instruction also helps us to reduce the binary size, since we don't need to implement the Ascon permutation in software anymore. And and if we compare the Ascon C implementation using the OS flag, we see that the binary size gets from 2104 byte down to 888 byte. For the Ascon hash implementation, we have similar performance numbers using our hardware instruction with only 4.6 cycles per byte for short messages and 2.1 cycles per byte for long messages, 2.5 cycles per byte for long messages. The binary size at 484 byte is even lower than for the Ascon encryption, since we use only since the Ascon encryption contains the associated data processing and the plaintext processing phases, whereas the Ascon hash doesn't need both of them. In terms of Isap, we tested the Isap A128A C implementation optimized for speed, which resulted in a tremendous 1184.3 cycles per byte for very short 64-byte messages. And with our hardware instructions, we could get that down to only 29.1 cycles per byte. For long messages, the C implementation did quite a bit better as well, with only about 352 cycles per byte. But with our hardware instructions, we could get it down to only 4.2 cycles per byte, which is only double of what we need for Ascon. And given that we have hardening against a range of implementation attacks, that makes it a quite competitive choice. Also, in terms of binary size, we could get Isap down to about 1,844 bytes, which is quite a bit lower than the 11,000 byte for the binary size. In terms of area, since we did a hardware design based on the RISC-V core, the RISC-V core itself uses 45.6 kilogate equivalent, only for the core itself. And our design adds 4.2 kilogate equivalent for the Ascon Accelerator, and also 0.5 kilogate equivalent for the integration that includes the wiring, basically the wiring between the Ascon Accelerator and the multiplexers for the register file. To put this into perspective to related work, we have the Ascon, there are two Ascon coprocessors out there, and both of them use 7.1 kilogate equivalent. They use 7.1 and 9.4 kilogate equivalent. However, that doesn't include the integration cost that would be necessary. Compared to the Isap coprocessor, they're all only estimated area. The area is only estimated, and it basically is specified as smaller than 12.8 kilogate equivalent. So overall, you can see that our work and also the reuse of the CPU register files can result in quite a difference in terms of overall area. Another interesting aspect of our accelerator is its implication on the implementation security of Isap. So Isap itself already offers protection or hardening against differential power analysis attacks, differential fault attacks, statistical fault attacks, and statistical ineffective fault attacks. And it's doing that purely on a mode level. If you want to know how exactly Isap manages to do that, I refer you to the specification for details. However, simple power analysis attacks are still possible, but due to the accelerator processing all of the 320 bits of the state at once, they are quite limited. With the accelerator in place, however, the state setup phase itself becomes the most lucrative target for an attack. And a localized EM analysis could allow for a successful simple power analysis attack. So to alleviate that, countermeasures like, for instance, shuffling should be added. For more details on a detailed analysis of how the attack works, I refer you to the section in our paper. So this brings us to the summary part of this presentation. And as a final remark, what I want you to take away from this presentation is that Ascon-p presents a very versatile building block for a wide variety of cryptographic primitives. And it also has shown that acceleration of one block can accelerate itself a wide variety of cryptographic primitives. So, and it even extends to with or without implementation security if desired. So, and the third point, one can get more performance and also better protection from implementation attacks. This brings us to the end of my presentation, and thank you for your attention.